All right, I've got a fun little puzzle for you today. What's the most efficient way to build any number using only perfect squares as your building blocks? Now, it sounds simple, but the solution? Oh, it reveals a really powerful problem-solving technique that can totally change the way you think about code and maybe a lot more.
So, let's start with a concrete example. Take the number 12. The goal is to add together the smallest possible number of perfect squares, 1, 4, 9, 16, those guys, to get exactly 12. I mean, sure, you could use 12 ones, but come on, we can definitely do better than that.
And the best answer is 3. 3 blocks of 4 give you 12. Simple enough, right? It kind of seems like the strategy is to just grab the biggest perfect square that fits and then work your way down.
But see, that greedy approach doesn't always work. Let's try it on the number 13. The biggest perfect square less than 13 is 9, so you grab that. What's left? 4. So 9 plus 4 ones? Wait, that's 5 blocks in total. Can we do better?
Oh yeah, we can. For 13, the best answer is just 2 blocks, a 9 and a 4. And this is huge because it proves that our first simple strategy of always taking the biggest piece, well, it's flawed. We need a smarter, more reliable system.
This is where the real puzzle starts. We need a method that's going to guarantee the best answer every single time, for any number we're given. So how do we build something like that?
Well, the key is to completely flip our thinking. Instead of starting with our big target number and trying to break it down, we're going to start from the bottom and build our way up. Like, if we know the best way to make the number 1, can that help us figure out the best way to make 2? And can those answers help us solve for 3?
This whole building up strategy has a formal name: dynamic programming. It's this incredibly powerful technique where you tackle a complex problem by just shattering it into smaller, simpler subproblems. You solve each tiny problem just once, write down the answer, and you never have to calculate it again. It's like you're doing a tough math problem, but you're keeping a cheat sheet of your results so you don't have to redo the work. It's all about efficiency.
So let's put this idea into practice with our first solution, which I like to call the methodical blueprint. It's a really clear, thorough way to see dynamic programming in action, and it uses a detailed table to track all our work.
Okay, so imagine a grid. Each row represents a new perfect square we get to play with. First, we can only use 1s, then we add 4s to our toolkit, then 9s, and so on. Each column is a number we're trying to build, from 1 all the way up to our goal. Our mission is to fill in this entire grid box by box.
Now, whoa, this formula might look a little intimidating, but trust me, it's just asking a really simple question for every single cell in our grid. The question is, should we use our newest perfect square or not? If we don't use it, the answer is easy. It's just whatever the answer was in the cell right above us. But if we do use it, we add 1 to our count and then look up the best answer for whatever number is left. We just pick whichever of those 2 choices gives us the smallest number of blocks. That's it.
Let's see it in action for the number 4. We ask ourselves, what's better, not using the square 4, which means we look at the answer from the row above, which was 4 ones, or using the square 4, which is 1 block, plus the answer for the number 0, which is 0 blocks. Well, a total of 1 is obviously better than 4. You see how we're constantly looking back at answers we've already figured out? We're reusing our work, never starting from scratch. That is the power of this approach. Okay, so that blueprint method works perfectly, but it uses a lot of memory to store that big 2D table. So can we do better? It turns out, yeah. After working through the first method, we can spot a really clever optimization that leads to a much more elegant solution.
So here's the key insight. To calculate any cell, you only ever need info from the row right above it and from cells to the left in the current row. We don't need the entire history. This means we can basically collapse our entire 2D grid down to a single one-dimensional array that we just update over and over. And the logic just simplifies so beautifully. To update the answer for our target number j, we just compare the current best answer we have for j with a new possibility, taking one of our square blocks plus the best answer we've already found for the remainder. We're just updating our answers in place, getting more and more optimal as we introduce bigger perfect squares into the mix. And here is where it all comes together. We start our array with the worst-case answers, just using the number 1. Then we make a pass with the number 4, and we update any spot where using a 4 gives us a better result. Then we do the same with 9. See? With each pass, our answers just get more and more refined, until we have the absolute best solution for every number up to our target. So, what's the big takeaway here? This is about way more than just a neat solution to a coding challenge. This puzzle gives us a powerful mental model for solving all sorts of complex problems. This is the dynamic programming mindset. You start small,
You build on what you already know. You store your results, so you're always working smarter, not harder. And then you refine your approach. You look for those clever insights, like going from a big table to a single row to make your solution not just correct, but truly elegant and efficient.
This technique of breaking things down and building from the bottom up applies so far beyond just code. So I'll leave you with this question. What's a big, messy problem in your life or your work that you could start chipping away at by finding the smallest, simplest piece